Imagine speeding down a cosmic highway, your vehicle ancient, delicate, and priceless, weaving through an endless field of invisible obstacles. That's the reality for 3 Atlas, currently navigating the asteroid belt with a caution that would humble even the most skilled driver. Except this vehicle isn't just old, it's 4 billion years old, carrying the chemical fingerprints of worlds far beyond our solar system. Every collision could obliterate evidence of alien matter that may forever remain unique in human history. And here's the kicker. This incredible journey isn't unfolding in some distant science fiction tale. We are witnessing it in real time. Each day, Atlas threads its path through the chaotic barrage of rocks between Mars and Jupiter, revealing a story of survival written across the void. This is no ordinary object hurtling through space. It is a rare interstellar traveler, and what makes its passage truly remarkable is that humanity has the privilege of observing every twist and turn. In this documentary, we follow Atlas as it faces the ultimate cosmic gauntlet, uncovering secrets that have existed for eons. By the end, we'll explore whether this ancient giant can survive one of the most treacherous crossings in our solar system, and what might unfold if it fails. And if you're drawn to journeys like this, floating through the universe without leaving your seat, your support through comments or sharing helps others find their way to these stories too. But for now, let's follow the trail of a traveler from beyond. On July 1st, 2025, in the arid peaks of Chile's Atacama Desert, a robotic sentinel named Atlas scanned the southern skies with meticulous precision. The Terrestrial Impact Last Alert System, its formal designation, had spent years cataloguing every celestial rock with the potential to threaten Earth. Yet that night, the telescope's sensors revealed something unexpected. A tiny flicker of light, faint and determined, moved steadily against the star-strewn canvas of Sagittarius. Within a single day, NASA's top astronomers had performed the calculations. What they found stunned the scientific community. This was no ordinary asteroid or comet. It was a messenger arriving from the stars themselves. They named it 3 Atlas, catalogued formally as CST 2025 N1. The 3 marking indicated it was only the third confirmed interstellar object humanity had ever observed. Pause for a moment and consider the magnitude of that. Throughout history, we've tracked billions of comets and asteroids, yet only 3 times have we identified travelers not bound to our sun's family. This was a visitor unlike any other. Identifying an interstellar object is not just about distance, it's about precise mathematics. When scientists traced Atlas's orbit backward through space and time, the results were staggering. Its trajectory defied the gravitational architecture of our solar system, revealing an orbit with an eccentricity of roughly 6.1. To put that in context, Earth's orbit is nearly circular, with an eccentricity of just 0.017. Even the most elongated comets from the distant Oort cloud rarely exceed an eccentricity of 1. Atlas, however, was moving along a hyperbolic path, an unmistakable signature of an object arriving from beyond our cosmic neighborhood. Its speed was equally extraordinary. Atlas barreled toward the sun at about 60 kilometers per second, over 200,000 kilometers per hour. No local gravitational interaction with Jupiter or Saturn could impart such velocity. This ancient traveler had been making its journey for millions, possibly billions of years, crossing the darkness between stars before arriving in our neighborhood. Tracing its origin was equally revealing. Backtracking Atlas's path led astronomers to the direction of Sagittarius, closer to the dense, ancient stellar populations near the Milky Way's core, not the sparse outer regions where our solar system resides. This suggested that the comet's chemical and physical makeup could be far older, far stranger than anything native to our system. What secrets might such a wanderer carry from regions of the galaxy far beyond our reach? Safety concerns emerged immediately, as is always the case when news spreads of objects approaching Earth, but there was no danger here. Atlas would make its closest approach to our planet in December 2025, a comfortable 1.8 astronomical units away, roughly 270 million kilometers, farther than Mars ever comes to us. Observers could watch in awe without fear. The Sun, however, would present a different story. Atlas was destined for a near encounter with our star, reaching perihelion between October 29th and 30th, 2025. At that point, it would skim just 1.36 to 1.4 astronomical units from the Sun, well within the orbit of Mars. For a traveler accustomed to the frozen emptiness of interstellar space, this confrontation with solar heat and radiation would be transformative. Already, signs of awakening were appearing. As the Sun's energy touched the ancient ices locked in Atlas's nucleus, sublimation began. A faint coma, a halo of gas and dust, started to form around the core, revealing the beginnings of a story written in real time. On August 27th, the Gemini South Telescope captured detailed color images of this emerging halo, uncovering hues that hinted at alien chemical compositions, unlike anything we've seen in our own solar system. Determining Atlas's size was tricky. Early estimates suggested a nucleus anywhere from a few kilometers to around 10 or 11 kilometers, larger than the first interstellar visitor, or Murmur, yet still small enough to fit within a large city. But physical dimensions alone failed to convey the significance of what was occurring. The comet's awakening represented humanity's first opportunity to witness extraterrestrial materials reacting to our Sun's influence, chemistry and physics that had developed in conditions utterly foreign to Earth. Every observation offered glimpses into processes shaped in alien stellar environments. This isn't just a fleeting encounter. Unlike previous interstellar visitors that passed quickly through our skies, Atlas promised a prolonged performance. For months it would remain within the reach of powerful telescopes and spacecraft, allowing scientists to study its composition, track its activity, and understand how an object forged in a distant star system interacts with our local sun. Yet what truly sets Atlas apart is its trajectory. It isn't merely interstellar. It is threading a perilous route through the most dangerous stretches of our solar system. Countless objects smaller than Atlas have disintegrated while attempting the same passage. Each asteroid and comet Atlas navigates is a potential hazard, a hidden trap that could end this extraordinary journey. Survival here is far from guaranteed. As Atlas moves onward, we are not just observers of a cosmic event. We are witnesses to a narrative billions of years in the making, a story of survival, chemistry and motion spanning light years. Every movement, every glimmering halo, every trajectory adjustment adds to a tale that will expand our understanding of the universe and our place within it. This is the dawn of a new chapter in human knowledge, an opportunity to connect with the material remnants of alien worlds and to explore mysteries that have traversed the galaxy to reach us. The asteroid belt awaited, a chaotic expanse of rocky fragments stretching between Mars and Jupiter, and for the first time, humanity had a front-row vantage to witness an interstellar traveler navigate this perilous passage. This is the story of 302 Atlas, and the questions surrounding its origin are as captivating as its journey itself. Where did this cosmic wanderer originate? The answer isn't written in stars but in numbers, encoded in the subtle shifts and patterns of its orbit across the galaxy. Astronomers meticulously rewound Atlas's trajectory, tracing its movement backward through space and time, and the results were astonishing. This was no random interloper, drifting aimlessly through the void. Its path aligned closely with the Milky Way's thick disk, an ancient stellar population formed during the galaxy's youth, when stars were born in turbulence and chaos. If this hypothesis is correct, Atlas could predate our solar system by billions of years, a relic of cosmic antiquity silently drifting, while our sun was still coalescing from clouds of gas and dust. The thick disk represents a middle-age phase of our galaxy, a time when metallic poor stars dominated, and planetary formation was far from uniform. Any planetary systems emerging in these environments would have been fundamentally different from our own, with lower concentrations of heavy elements, altered chemical abundances, and unfamiliar physical conditions. Comets born in such neighborhoods would carry signatures unlike anything native to our solar system, frozen records of alien chemistry across billions of years. But how does a comet become an interstellar traveler in the first place? The answer lies in cosmic chaos. Forming planetary systems are battlegrounds, arenas of gravitational turmoil. Massive planets migrate inward and outward, scattering smaller bodies into space. Encounters between stars can gravitationally rip comets from their parent systems, and close approaches with massive objects can hurl icy worlds onto hyperbolic trajectories, sending them across the galaxy. Models suggest that for every comet bound to its star, dozens or even hundreds are ejected, wandering the cosmic ocean indefinitely. Multiply this by billions of planetary systems, and the galaxy teems with these interstellar voyagers. Atlas is not alone. It represents just one among countless objects journeying through the void. Initial observations revealed intriguing insights into Atlas's physical characteristics. Photometric data suggested a nucleus somewhere between 10 and 20 kilometers in diameter, far larger than Nugamor, the first interstellar visitor, which spanned only a few hundred meters. Size matters here. Bigger comets retain volatile ices longer, resisting the destructive forces of stellar heat and radiation more effectively. Yet the most remarkable revelations came from chemical analysis. The James Webb Space Telescope trained its infrared instruments on Atlas's emerging coma, revealing an extraordinary environment rich in carbon dioxide. The ratio of carbon dioxide to water vapor measured around 8:1, an extreme value unseen in most solar system comets. This chemical fingerprint hints at alien formation conditions. Carbon dioxide ice dominates only under specific circumstances, either forming near the CO5 ice line of a protoplanetary disk, or through prolonged exposure to galactic cosmic rays over millions of years, transforming water ice into other compounds. Both scenarios imply an origin fundamentally distinct from the comets we are familiar with. Speculation followed. Some researchers suggested Atlas might have been expelled from a low metallicity red dwarf system, rather than a sun-like star. Red dwarfs dominate the thick disk population, with planetary systems shaped under unique chemical and thermal conditions. Habitable zones are closer, disks cooler, ultraviolet output lower, preserving ice compositions that would rapidly change in solar-type environments. These factors could explain Atlas's unusual chemistry, but testing these theories would require in-depth spectroscopic analysis as the comet approached the Sun. Polarimetric measurements added further intrigue. Early studies showed light scattering patterns unlike typical solar system comets, hinting at differences in particle size, surface texture, or composition within the coma. These subtle clues offer a window into the internal structure and formation history of an object that has endured eons in interstellar space, carrying records of physics and chemistry that predate our planetary neighborhood. Comparisons to prior interstellar visitors underscore Atlas's uniqueness. 2I/Borisov, discovered in 2019, behaved much like familiar solar system comets, a foreign object that still fit known patterns. Oumuamua, conversely, displayed no classic cometary activity and exhibited unexplained non-gravitational acceleration, sparking debates about its true nature, with some theories suggesting it was a fragment of a disrupted planetary body. Atlas occupies a middle ground. It behaves as a comet, actively producing gas and dust, yet its chemical signature is unmistakably alien. This duality makes it both familiar enough to analyze scientifically and foreign enough to expand our understanding of planetary formation across the galaxy. Many mysteries remain. The precise dimensions and shape of its nucleus are still uncertain, awaiting high-resolution imaging as the comet brightens. Its rotation rate and axis tilt are unknown, yet these factors will dictate how material is shed, whether evenly or asymmetrically. Beyond carbon dioxide and water, the full chemical inventory remains hidden, pending more sensitive spectral observations. Perhaps most crucially, no one can predict exactly how its activity will evolve as it draws closer to the Sun's warmth. The coming months promised unprecedented opportunities. The Hubble Space Telescope scheduled regular monitoring sessions, ground-based observatories, including 8 10-meter class telescopes, coordinated campaigns to track compositional and activity changes. Multiple spacecraft within the inner solar system positioned themselves to provide complementary perspectives. Every measurement would be historic. The first chance to observe extraterrestrial chemistry responding to solar radiation, to monitor alien materials in real time, and to compare formation signatures from vastly different galactic environments. Atlas was more than a comet. It was a living time capsule, carrying chemical and physical imprints from ancient stellar neighborhoods far removed from our own. Observing it offered a glimpse into processes that unfolded billions of years ago, in regions where stars and planets evolved under conditions radically different from the Sun's environment. Each new piece of data brought us closer to understanding the diversity of planetary formation throughout the galaxy. Yet before scientists could decode these cosmic messages, Atlas faced a trial by fire. The asteroid belt loomed ahead, a hazardous expanse that has shattered countless smaller objects over the eons. Its survival was far from guaranteed. Every kilometer traversed would test the comet's resilience, pushing it to endure collisions, radiation, and gravitational perturbations in a region notorious for destroying the unprepared. Humanity watched, poised on the edge of discovery. For the first time, a spacecraft was not required to witness the drama of interstellar chemistry in action. A frozen relic of the galaxy, billions of years old, would demonstrate how materials forged in alien systems respond when confronted with our sun, the planets, and the unpredictable hazards of our solar system. His journey through the asteroid belt was more than a navigation feat. It was a window into the cosmos, a rare bridge between alien history and human observation. And so, Atlas began its crossing, carrying the secrets of an ancient galaxy through the perilous lanes of our celestial neighborhood. A voyage that would reveal not only the nature of its origin, but also the fragility and resilience of interstellar wanderers as they encounter the blazing furnace at the heart of our solar system. Between Mars and Jupiter stretches a region that has fascinated astronomers and storytellers alike for centuries. The asteroid belt, populated by millions of objects, each silently tracing an orbit established over 4.5 billion years. This zone represents a relic of the early solar system, a cosmic museum frozen in time. For a comet like 32 Atlas, hurtling through the solar system on a hyperbolic trajectory from interstellar space, the belt is far more than a scenic backdrop. It is a vast gauntlet of potential hazards, a corridor where the risks are immediate and tangible. Survival in this region is not a given. It requires navigating a field shaped by eons of gravitational dance, collisions, and chaos. And yet, for the first time, humanity could observe this extraordinary crossing, witnessing an alien object confront a part of our solar system in ways no spacecraft has ever experienced. Science fiction has long dramatized the asteroid belt, portraying it as a perilous minefield, where every second is a matter of life and death. Heroes weave through tumbling rocks, narrowly avoiding collisions, their ships buffeted by the constant threat of destruction. While these depictions capture the imagination, reality is far subtler, yet no less intriguing. Space, even in its densest regions, remains overwhelmingly empty. Although millions of rocks inhabit the belt, from massive dwarf planets to tiny dust grains, the distances between significant objects often span millions of kilometers. Imagine Earth's orbit as a cosmic highway. The asteroid belt is like a stretch where vehicles are spaced by thousands of kilometers, sparse enough that collisions are rare, but each encounter has consequences far beyond the mundane. NASA's missions have repeatedly traversed this region, demonstrating that with careful planning, the belt poses little hazard to spacecraft. Yet Atlas does not follow conventional routes. Most asteroids orbit the Sun in prograde motion, moving in roughly the same direction as the planets. Atlas, however, is on a retrograde trajectory, inclined at approximately 175 degrees relative to the ecliptic plane. In simpler terms, it is racing almost directly against the natural traffic of the belt. This creates relative velocities far higher than what is typical in the solar system, where most objects gently co-orbit. Any collision, even with a small fragment, could produce catastrophic results because the kinetic energy increases exponentially with speed. Tens of kilometers per second are enough to shatter or fragment even a multi-kilometer nucleus. The belt itself is far from homogeneous. Its densest regions cluster near the ecliptic plane, the imaginary surface that also hosts Earth and nearly all planetary orbits. Atlas, despite its steep inclination, will intersect this populated layer, slicing through the heart of the belt rather than skimming safely above or below. Within this zone, diversity reigns. The largest residents, Ceres, Vesta, Pallas, and Hygiea, are more than geological curiosities. They are massive enough to retain roughly spherical shapes and display complex histories, including differentiation and volcanic activity. Beneath them lies a vast population of irregular fragments, the remnants of ancient collisions, each bearing chemical clues about the solar system's formative era. These smaller bodies come in a wide range of compositions. Fender P-type asteroids are carbon-rich, dark, and primitive, preserving material from the solar nebula's outer regions. Site types, likely fragments of differentiated bodies, provide evidence of past molten interiors. Rare M-types consist almost entirely of metal, possibly representing exposed planetary cores from cataclysmic collisions. Some objects are immigrants, scattered inward from the outer solar system during planetary migration events, highlighting the dynamic reshaping that occurred over billions of years. For Atlas, each type of object represents a different potential interaction. Yet the greatest threats are not the massive, named asteroids, but the innumerable smaller fragments, from meter-scale boulders down to dust grains, micrometers in size. Individually, these fragments are too tiny to track, but collectively they create a hazard that is both pervasive and subtle. The dust component of the belt warrants particular attention. Continuous collisions among larger objects generate a steady flux of fine particles which gradually spiral sunward under radiation pressure. For an active comet like Atlas, which develops a coma and tail as it approaches the sun, this dust creates a microscopic sandblasting effect, gradually eroding surface material and reshaping the outer layers of the nucleus. The interaction between dust, solar radiation, and the comet's ionized environment adds layers of complexity. Tiny charged particles respond not only to gravity, but also to electromagnetic forces, producing waves, instabilities, and intricate structures within the coma. This transforms the asteroid belt from a simple collection of obstacles into a dynamic, three-body system where gravity, radiation, and electromagnetism interplay to create unpredictable behavior. Observing these processes in real time would provide unprecedented insights into comet dust interactions, plasma physics, and the response of alien materials to our solar environment. Despite these hazards, statistical modeling strongly favors Atlas's survival. NASA and other institutions have calculated collision probabilities for objects of its size. While the belt is dense by human standards, the odds of catastrophic impact are vanishingly small. In essence, the belt is more like an ocean peppered with isolated islands than a densely packed minefield. However, vanishingly small is not zero. For a comet carrying unique extraterrestrial chemistry, even minor interactions hold significance. Micro-impacts could trigger local outbursts, temporarily altering brightness or disturbing coma structure. Dense dust regions might sculpt the tail into unusual shapes, offering clues about solar wind conditions and the interaction between alien materials and electromagnetic forces. From an observational standpoint, this crossing was a goldmine. Wide-field surveys could continuously monitor Atlas as it passed through different belt sectors, looking for subtle activity changes. Spacecraft equipped with solar wind and particle detectors could correlate tail structures with heliospheric variations. Each disruption, each interaction, presented a unique opportunity to map previously unseen dust concentrations, study plasma behavior, and investigate how an interstellar object responds chemically and physically to conditions entirely different from its birthplace. The asteroid belt became, for a brief window, a laboratory for alien materials. Atlas's retrograde trajectory introduced additional challenges. While most comets gently co-orbit with the planets, Atlas is hurtling almost directly against the flow of local debris. The relative velocity between the comet and native belt objects can exceed tens of kilometers per second, increasing the destructive potential of any impact. Even small particles, traveling at such speeds, carry immense kinetic energy. Fortunately, vast separations between sizable asteroids still provide a buffer, but for micrometeorites and dust, continuous erosion is inevitable. Every grain strikes with sufficient force to modify surface ice and dust layers, subtly altering the way volatiles are released and potentially producing temporary spikes in activity detectable by telescopes. The size, composition, and activity of Atlas make these interactions scientifically fascinating. Its nucleus, significantly larger than looming armor but smaller than most planetary satellites, carries volatile compounds formed in conditions unlike anything in our solar system. Observing how these materials react to dust collisions, solar heating, and electromagnetic forces, offers insights into interstellar chemistry, the longevity of volatile compounds in alien environments, and the physical processes shaping cometary evolution over billions of years. Further complicating matters, the belt is not static. Objects move along intersecting paths, some on eccentric orbits, some influenced by resonances with Jupiter's gravity. Atlas, with its hyperbolic speed and extreme inclination, will traverse these dynamically evolving corridors in hours what the belt's residents traverse in centuries. This amplifies the relative motion, meaning even minor debris clouds could produce localized shock events or temporary coma disturbances. Each phenomenon represents a chance to study interactions that are impossible to replicate in laboratories on Earth. Dust-plasma interactions also provide a rare observational advantage. As grains encounter the comet's ionized coma, electromagnetic forces generate waves, streams, and irregularities that reveal the structure and density of the solar wind and magnetic field at unprecedented resolution. These effects could also offer clues about the composition and size distribution of dust in the asteroid belt, a dataset otherwise nearly impossible to collect from Earth alone. The crossing also poses questions about cometary resilience. How does a nucleus with alien ices withstand continuous microabrasion and high-speed particle impacts? Do these processes trigger localized outgassing, forming jets that alter rotational dynamics or accelerate sublimation? Could variations in tail morphology reveal hidden asymmetries within the nucleus, or even indicate structural weaknesses inherited from its ancient formation environment? Every interaction, no matter how minor, is a potential key to understanding not only Atlas, but also the broader population of interstellar objects silently traversing the galaxy. Yet for all the risks, survival is statistically the expected outcome. Millions of kilometers separate most major asteroids, and the majority of impacts involve particles too small to significantly damage a nucleus of Atlas's size. The crossing is as much about opportunity as it is about hazard. Astronomers can watch an interstellar object navigate a densely populated region, studying real-time responses of alien chemistry to local conditions, mapping fine-scale structures of the belt, and gathering data on processes that occur only in deep space. In essence, Atlas transforms a potentially deadly journey into a scientific treasure trove. The retrograde path also allows for unprecedented calibration. By observing how dust and microfragments interact with the comet's tail under extreme relative velocities, scientists can test models of plasma dynamics, radiation pressure effects, and microcollision physics. These measurements have implications beyond the solar system, offering a benchmark for understanding interstellar dust, comet evolution, and the mechanisms by which objects lose material while traversing hostile environments. In the end, the asteroid belt's greatest gift to humanity may not be the challenge it poses, but the laboratory it provides. Atlas's passage enables direct observation of alien chemistry under stress, offering a window into processes that shape distant planetary systems. Each micro-impact, tail distortion, and coma fluctuation conveys information about the belt, the comet, and the solar wind in a single experiment conducted on a cosmic scale. As Atlas threads its way through this ancient debris field, we are not merely spectators. We are witnesses to a collision of timescales, physics, and chemistry. A relic of the galaxy's youth, shaped by conditions far from our sun, is interacting with the oldest neighborhood in our solar system. Each kilometer traveled, every microscopic encounter with dust, each subtle shift in the coma or tail, is a chapter in a story billions of years in the making. The asteroid belt is more than a barrier. It is a proving ground, a canvas on which the forces of the solar system will paint patterns in alien material, revealing secrets that have been locked away since the formation of the Milky Way itself. In this crossing, Atlas embodies the bridge between alien formation environments and our observational reach. The comet is a storyteller, narrating eons of chemical and physical history through its reactions to the asteroid belt's hazards. Its passage allows scientists to probe interstellar chemistry, test dynamic models, and witness firsthand the behavior of a hyperbolic traveler within the complex environment of a planetary system. Every interaction, no matter how fleeting, contributes to a narrative that will expand our understanding of both comets and the broader mechanics of the galaxy. As Atlas drew ever closer to the inner solar system, observatories across the globe prepared for a historic sequence of observations. Instruments were carefully calibrated, observation schedules meticulously planned, and spacecraft positioned to provide complementary viewpoints. The asteroid belt, once considered merely a distant curiosity, had become the first real test of this ancient traveler's resilience. Here, a relic from the depths of interstellar space would confront conditions that had never threatened it before, facing not only potential collisions with debris, but also the complex forces of solar radiation, plasma interactions, and gravitational perturbations. Humanity had never before witnessed an object of alien origin in such a vulnerable state. For the first time, we were watching an interstellar visitor as it navigated the hazards of a planetary system, observing history unfold in real time. The transformation of Atlas began subtly, almost imperceptibly, yet with profound implications. Initially, the object appeared as a faint point of light, almost indistinguishable from the countless stars scattered across the celestial sphere. Its slow, steady drift revealed that it was moving against the fixed backdrop of the galaxy, a hint of its interstellar origins. But as days passed and solar radiation intensified, the comet began to awaken. Deep within its nucleus, ancient ices, frozen for billions of years in the darkness between stars, started to respond to the sun's warmth. The process itself is simple in principle, but extraordinary in consequence. Sunlight heats the nucleus, causing ices to sublimate directly into gas. The escaping molecules carry embedded dust grains outward, forming a diffuse atmosphere around the comet known as a coma. Unlike a conventional atmosphere bound by gravity, this cloud can expand to dimensions larger than entire planets, transforming a modest icy body into a luminous spectacle spanning millions of kilometers. But Atlas was producing a coma that was far from ordinary. Observations from the James Webb Space Telescope revealed that carbon dioxide, not water vapor, dominated the outgassing. In most solar system comets at comparable distances from the Sun, water sublimation is the primary driver of activity, with carbon dioxide playing a secondary role only when farther from the star. Atlas's unusual composition immediately distinguished it as alien, a product of chemical conditions and formation processes unlike anything in our local neighborhood. This early activity carried significant implications. Carbon dioxide sublimates at lower temperatures than water ice, which meant that Atlas began producing a visible coma while still relatively distant from the Sun. This suggested that its surface or near-surface layers were unusually rich in volatile ices. Alternatively, it could indicate the presence of internal heating mechanisms, perhaps inherited from past cosmic radiation exposure or structural stress accumulated over eons of interstellar travel. In either scenario, Atlas was defying the behavioral patterns familiar to astronomers, signaling that its response to solar radiation would be unpredictable and potentially more dramatic than typical comets. As the coma expanded, the interplay of solar radiation and the solar wind sculpted it into more complex structures. Photons striking dust grains impart momentum, gently pushing particles away from the Sun to create a dust tail that curves along the comet's orbital path. Meanwhile, the solar wind, a continuous stream of charged particles emanating from the Sun, interacts with ionized gases in the coma, sweeping them into a plasma tail that points directly away from the Sun, independent of the comet's motion. The result is the iconic dual-tail structure that makes comets both beautiful and scientifically rich. For Atlas, the tail was both a symbol of triumph and a reminder of fragility. Each particle shed represented material that had survived billions of years of cosmic radiation, collisions, and interstellar drift, now being carried away during its brief encounter with our Sun. The dust tail reflected sunlight gracefully along the comet's trajectory, while the plasma tail extended millions of kilometers, dynamic and sensitive to variations in solar wind density and magnetic field strength. These interactions transformed the comet into a real-time monitor of heliospheric conditions, a cosmic weather station providing data impossible to reproduce in terrestrial laboratories. The plasma interactions introduced additional layers of complexity. Charged particles in the solar wind transfer momentum and energy to ionized gases in the coma, creating localized magnetic field enhancements and wave structures that propagate both upstream and downstream from the comet, Coronal mass ejections or high-speed solar wind streams can temporarily disrupt or even disconnect the plasma tail, only to allow it to reform as conditions stabilize. Atlas's carbon dioxide-dominated chemistry produced behaviors distinct from typical water-rich comets, potentially generating new wave phenomena, instabilities, and subtle plasma effects that have never been observed before. However, not all aspects of the developing tail were reassuring. Early activity exhibited significant asymmetry, with jets and outbursts originating from discrete regions rather than a uniform release across the nucleus. Such uneven outgassing can generate torque, altering the comet's rotation and potentially causing tumbling motions. Over time, this could introduce structural stress, exacerbating the natural weakening of the nucleus and increasing the risk of fragmentation. The beauty of the glowing tail masked the underlying tension within the nucleus, revealing that while Atlas's ices were alive and dynamic, they were also undergoing mechanical strain. Observations from ground-based telescopes reinforced this picture. Brightness curves showed irregular spikes, indicative of discrete outbursts rather than smooth, steady activity. High-resolution imagery captured narrow jets and localized plumes within the coma, evidence of non-uniform venting that suggested pockets of volatile material or structural anomalies beneath the surface. Each change, each flare, provided a glimpse into the hidden architecture of the comet, revealing a body both ancient and fragile, newly exposed to conditions never encountered during its interstellar odyssey. The timing of these developments was critical. Atlas was still approaching the asteroid belt, a zone that, while statistically not densely packed, represents a significant hazard due to the sheer number of small particles and the possibility of high-speed micro-impacts. Any irregularity in the comet's rotation or localized weakening could amplify the consequences of even minor collisions, potentially altering the coma, producing outbursts or modifying the tail in ways that would be detectable from Earth. In this sense, the tail served as both a diagnostic tool and a warning system, offering clues about internal stresses before the comet faced the additional challenges of the belt. Yet these warning signs were simultaneously scientific boon. Every spectral line, every flare in brightness, every shifting jet provided unparalleled information about the nature of interstellar ices and their response to solar radiation. Observing how Atlas's exotic chemistry reacted to external stimuli offered a direct window into processes that had occurred billions of years ago, in conditions completely alien to our own solar system. The asymmetries and outbursts, while potentially signaling structural stress, also allowed astronomers to test models of sublimation, plasma interactions, and tail formation under extreme conditions. By monitoring the dual tail structure, scientists could correlate variations in dust and ion behavior with solar wind measurements, identifying not only the composition of the cometary material, but also the response of interstellar ices to electromagnetic and gravitational forces. The interaction of carbon dioxide ions with the solar wind introduced subtle but detectable deviations in plasma flow, a phenomenon never recorded in prior comet observations. The evolving tail became a dynamic laboratory, where both the composition of the comet and the properties of the solar wind could be studied simultaneously in real time. As Atlas continued its approach, the cumulative effects of asymmetric outgassing became increasingly apparent. Torque generated by localized jets began to alter its rotation gradually, producing minor wobbling that could influence future sublimation patterns. Each plume added momentum, redistributing surface material and modifying internal stress. Brightness variations, though visually striking, were also a subtle record of mass loss, offering quantitative insights into how a hypervelocity interstellar object responds to solar heating for the first time in billions of years. Simultaneously, the comet's tail provided critical observational opportunities. Variations in plasma structure revealed not only the composition of the outgassed materials, but also the fine-scale distribution of charged particles in the surrounding solar wind. Dust grain ejections traced the interaction of radiation pressure with micron and millimeter-scale particles, offering a natural probe into the physics of small-scale collisions and dust dynamics in the inner solar system. Every feature, from the faintest jet to the most dramatic kink in the plasma tail, contributed to a richer understanding of cometary physics in both local and interstellar contexts. The cumulative picture emerging from observations painted Atlas as an object under extraordinary stress, simultaneously delicate and resilient. Its ancient ices were sublimating, forming spectacular tails and dynamic jets, yet the nucleus itself appeared to be coping with forces and conditions for which it had never been designed. The asymmetries, irregular activity, and plasma interactions were not just curiosities. They were a narrative of survival, revealing how a relic from another star system adjusts to an entirely new environment. At this stage, the question facing astronomers shifted. No longer was the focus solely on whether Atlas would survive the asteroid belt. The more pressing issue became understanding the interplay between its internal structure, unusual chemistry, and external forces. How would ongoing sublimation, torque from asymmetric jets, and plasma interactions influence its trajectory or rotation as it approached increasingly hostile regions? Could minor instabilities escalate into fragmentation, or would the comet prove sufficiently robust to endure these new challenges? Each observation offered clues, allowing scientists to anticipate potential behavior and plan further monitoring strategies. In essence, Atlas's growing tail had become both a warning signal and a scientific instrument. The comet's response to solar radiation, the shape and composition of its dual tails, and the dynamics of localized outbursts provided a real-time window into phenomena previously accessible only through simulation. The interplay of dust, gas, plasma, and electromagnetic forces formed a complex evolving system, revealing processes that link interstellar chemistry, solar physics, and cometary dynamics. Humanity was witnessing not merely a celestial display, but the first detailed observation of an interstellar object reacting to a star, offering unparalleled insight into the composition and physics of alien worlds. The patterns of activity Atlas displayed were already defying expectations. Jets erupted unevenly across its surface, brightness fluctuated unpredictably, and the twin tails expanded with irregular morphology. Yet ahead loomed the greatest challenge of its journey, the asteroid belt, a treacherous gauntlet that could determine whether this ancient wanderer would survive long enough to reveal its secrets. The growing coma and tail, so stunning from Earth, also marked vulnerability. Each particle stripped away by solar radiation or plasma interactions represented a fragment of a record formed billions of years ago, material that would never return. For the first time, humanity was poised to witness how a truly interstellar object responds when exposed to the combined hazards of a crowded planetary system. Before confronting the belt, it helps to reflect on Atlas's predecessors. Interstellar objects are rare, and each has told a story of extraordinary differences. The first confirmed visitor, 1I/Oumuamua, emerged in October 2017, detected racing through the inner solar system by the Pan-STARRS survey in Hawaii. Its name, meaning messenger from afar arriving first, was both fitting and prophetic. Oumuamua was unlike anything astronomers had ever seen. Its extreme elongation, roughly 10 times longer than wide, hinted at either highly unusual natural processes or, as some speculated, artificial origin. Even more confounding, it showed no visible coma or tail despite passing within Earth's orbit, leaving its composition a mystery. Tracking Oumuamua's departure revealed another puzzle. Telescopes measured a persistent small acceleration inconsistent with gravity alone. Outgassing of invisible gases was suspected, yet no emission was directly observed. Later models suggested possibilities ranging from sublimation of undetectable hydrogen ice to the hypothesis that it might have been a fragment of a Pluto-sized object disrupted by stellar encounters. Whatever the mechanism, it challenged the understanding of what a natural interstellar object could do, highlighting that alien formation environments could produce phenomena unseen in our solar system. The second confirmed interstellar visitor, 2I/Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, presented a stark contrast. Borisov behaved much like a familiar solar system comet, developing a bright coma and a well-defined tail. Spectroscopic analysis revealed water vapor, carbon monoxide, and hydrocarbon ratios comparable to comets from our own Oort cloud. Its nucleus remained intact throughout the solar encounter, and its activity followed predictable solar heating models. Where Oumuamua was enigmatic, Borisov was reassuringly ordinary, a visitor confirming that planetary systems beyond our own could produce objects chemically and physically similar to those we know. Atlas, however, occupies a unique position between these extremes. Like Borisov, it exhibits typical cometary activity, developing a coma and dual tails as it nears the Sun. Like Oumuamua, it reveals unfamiliar chemical signatures and structural anomalies that challenge existing models. Its carbon dioxide-dominated outgassing, the unusual ratios of volatile ices, and the asymmetric jets all suggest formation in an environment fundamentally different from our solar system. While visually reminiscent of a solar system comet, Atlas carries an entirely alien narrative written in its composition, rotation, and interaction with solar forces. Trajectory comparisons further highlight its uniqueness. Oumuamua entered at a steep angle to the ecliptic, passing largely unimpeded by planets or major debris, leaving little opportunity for study. Borisov approached on a more moderate path, avoiding the densest regions of the solar system while still offering extended observation time. Atlas, by contrast, is threading a near-ecliptic retrograde course directly through the asteroid belt, the most densely populated segment of the inner solar system. This route maximizes interaction with both solid objects and the structured solar wind environment, creating unprecedented observational opportunities while increasing potential risks. Historical precedent offers both reassurance and caution. Comets from the solar system, such as CES 2023 A3, Sachin-Chan, have survived dramatic tail disconnections caused by coronal mass ejections. Observations from SOHO and other heliophysics missions document how solar wind interactions routinely fragment and reform comet tails without destroying the nucleus. These events demonstrate that dramatic tail activity is not inherently fatal, yet they also underscore the delicate balance required for survival. Atlas's novelty lies in its combination of unusual chemistry, retrograde motion, and passage through a densely populated region, variables not previously observed simultaneously. From a scientific perspective, Atlas represents a breakthrough. Its chemical composition allows spectroscopic study of alien ices reacting to a local star. Its tail morphology and asymmetries reveal the mechanical stresses experienced by an object that has drifted for billions of years in interstellar darkness. Its journey through the belt offers a natural laboratory for understanding dust interactions, plasma dynamics, and the response of alien materials to both gravitational and electromagnetic forces. Each observation feeds into models of planetary formation, interstellar chemistry, and heliophysics, providing insight into questions that would otherwise remain theoretical. Yet despite the promise, danger is unavoidable. Unlike its predecessors, Atlas must contend with the asteroid belt, a region populated with millions of objects ranging from dwarf planets down to dust grains. While space remains mostly empty even here, the high relative velocity created by Atlas's retrograde trajectory, nearly opposite the motion of local asteroids, magnifies the energy of any potential collision. Kinetic energy scales with the square of relative velocity, so even a minor impact could have consequences far exceeding those typically observed in solar system cometary interactions. The geometry of its approach compounds the challenge. Atlas entered the observable solar system from the direction of Sagittarius, initially faint, with apparent magnitude between 16 and 18. As it accelerates inward from roughly 3 to 5 astronomical units, it will traverse the asteroid belt's core, reaching perihelion at 1.357 astronomical units by late October 2025. Observing this path requires precision. Initially, professional telescopes track the dim object across constellations like Sagittarius and Ophiuchus, but as the comet brightens, smaller instruments can join in, providing complementary coverage. Planetary proximities add further interest. Atlas will pass approximately 0.19 astronomical units from Mars on October 3, 2025, roughly 28 million kilometers. While too distant for collision, this offers Mars-orbiting spacecraft an ideal vantage point to observe tail dynamics and measure outgassing. Later passages include Venus at 0.65 astronomical units on November 3rd and Jupiter at 0.36 astronomical units on March 16, 2026. These flybys will not significantly alter its hyperbolic trajectory, but they provide opportunities for triangulation, parallax measurements, and cross-observatory coordination, enhancing the quality and resolution of collected data. Earth's distance remains safe, with closest approach in December 2025 at 1.8 astronomical units, or roughly 270 million kilometers. Any debris from fragmentation would follow the hyperbolic path, missing our planet entirely. Velocity adds another layer of complexity. Atlas's hyperbolic excess velocity, the speed it carries in interstellar space far from gravitational influence, is approximately 58 kilometers per second. As it falls toward the Sun, gravitational acceleration increases this, creating relative velocities with asteroid belt objects exceeding 100 kilometers per second. To contextualize, the Parker Solar Probe, humanity's fastest spacecraft, reaches about 190 kilometers per second at perihelion. Atlas maintains a comparable fraction of that speed naturally, having traveled uninterrupted across millions of years, making its navigation of the inner solar system a feat unmatched in human engineering. Its retrograde, near-ecliptic course ensures maximum interaction with the most populated and electromagnetically complex regions of the solar system. The ecliptic plane hosts both the densest concentration of solid bodies and the most structured solar wind environment. Coronal mass ejections, co-rotating interaction regions, and other solar phenomena are amplified here, presenting conditions that are not only physically demanding, but also scientifically rich. Each micro-interaction, dust-particle collisions, plasma flux, jet torque, provides real-time data about both the comet and its environment. In short, Atlas is threading a cosmic needle. Its retrograde trajectory, alien chemistry, dual-tail structure, and asymmetrical outgassing place it in an environment more challenging than anything previously observed. Its predecessors provide context, illustrating both the possibilities and the limitations of interstellar objects entering our system. Yet no prior visitor has combined these extremes into a single object, a chemically alien comet navigating a densely populated, electromagnetically complex region while remaining under constant solar heating and observational scrutiny. The stage is set for a journey that transcends ordinary comet science. Every photon captured, every subtle shift in brightness, every kink in the plasma tail is a data point in an unprecedented narrative. Humanity will watch, document, and analyze in real time as Atlas confronts the asteroid belt, negotiates solar wind pressures and survives, or succumbs to, the complex forces that govern planetary systems. In doing so, we witness not just a comet, but a messenger from another star system revealing the physics, chemistry, and history of a galaxy beyond our own. As Atlas pressed onward, heliophysics researchers recognized an unparalleled opportunity. Its path offered a real-time experiment, how an interstellar comet responds when threading through varied regions of the heliosphere. Spacecraft scattered across the inner solar system could simultaneously capture different perspectives, constructing a three-dimensional view of its coma and tail, a perspective unattainable from ground-based observatories alone. The comet's trajectory also favored terrestrial telescopes. Unlike previous visitors that approached from steep inclinations, offering mere fleeting glimpses, Atlas remained visible over months. This afforded astronomers the luxury of repeated measurements, seasonal coverage from both hemispheres, and redundancy against adverse weather, ensuring no significant event went unnoticed. The route itself provided unique scientific value. During July and August, Atlas crossed the outer asteroid belt, a relatively pristine environment with minimal solar wind influence, establishing baseline activity and composition. September's passage through the belt's densest regions introduced interactions with both dust and larger bodies, revealing how the comet responds to localized collisions and gravitational perturbations. In October and November, as it entered the inner solar system, Atlas would experience peak solar radiation, testing the structural resilience of its nucleus while exposing its volatile ices to extreme heating. The retrograde orbit offered another observational advantage. The comet's apparent motion against background stars was amplified, improving positional accuracy and simplifying spectroscopic separation from stellar contamination. Yet the same features that make the trajectory scientifically invaluable also heighten risk. Each day brought Atlas closer to the asteroid belt's most densely populated regions. The gauntlet it faced was not merely navigational, it was existential. Orbital mechanics had engineered a perfect natural experiment, a hypervelocity interstellar object, threading through a region dense enough to interact with dust and minor bodies, yet vast enough for survival to remain probable. Humanity had front-row seats to witness the outcome. The belt itself houses some of the solar system's most iconic residents. Ceres, Vesta, Pallas, and Hygiea dominate the region. Ceres, nearly 1,000 kilometers across, has achieved hydrostatic equilibrium, earning dwarf planet status. Vesta, with its irregular shape and ancient impact basins, preserves the scars of early planetary collisions. Pallas and Hygiea, though slightly smaller, exert measurable gravitational influence, shepherding nearby debris into stable orbits over billions of years. These colossal bodies are the anchors around which millions of smaller fragments orbit. For Atlas, however, these giants posed virtually no threat. The immensity of space means even objects of thousands of kilometers are separated by millions of kilometers from each other. To illustrate, if Earth were a marble in New York City, Ceres might be another marble in Los Angeles, the intervening distance overwhelmingly empty. NASA's collision probability assessments affirm this, showing risks so minute that they are almost meaningless. Every spacecraft traversing the belt, from Pioneer 10 to the latest Mars missions, has passed without a single significant impact, underscoring the disconnect between cinematic depictions and reality. Yet Atlas's retrograde path changes the dynamics dramatically. By traveling against the flow of the belt's resident objects, relative velocities can exceed 100 kilometers per second. While chance encounters remain statistically minuscule, the energy involved in any collision would be extraordinary. Kinetic energy scales with the square of relative speed, thus even a small fragment striking at such velocity would unleash the equivalent of multiple nuclear detonations. A direct hit on the nucleus from anything larger than a pebble could completely disintegrate the comet. The implications are both thrilling and terrifying. A significant collision would produce a fleeting brilliance observable from Earth, as the nucleus shattered into countless fragments, each continuing along independent hyperbolic paths out of the solar system. The delicate record of ancient interstellar chemistry would vanish instantly. Despite public concern over hypothetical Earth-crossing fragments, orbital mechanics guarantees safety. Atlas's hyperbolic energy is simply too high for Jupiter, Mars, or any other solar system body to deflect it significantly. Debris would continue on escape trajectories, returning to the interstellar void from whence it came. The true danger lies elsewhere. The countless minor fragments populating the belt, from centimeter-scale pebbles to meter-sized rocks. The development of Atlas's coma and tail expands its effective cross-sectional area from mere kilometers to potentially hundreds of thousands of kilometers. While collisions with individual grains are unlikely to destroy the nucleus, they can disrupt the coma's structure, trigger localized outbursts, or alter tail morphology. Observers on Earth could witness sudden brightness spikes, asymmetric jet formation, or tail distortions, direct evidence of micro-impacts. These events, though subtle, provide unparalleled insight into both the comet's internal mechanics and the previously invisible small particle population of the asteroid belt. Gravitational perturbations present another subtle hazard. While a direct collision with Ceres or Vesta is virtually impossible, their gravitational influence could modify Atlas's spin rate, slightly adjust its rotational axis, or stress internal structures in ways that might encourage fragmentation. Equally intriguing, the belt contains immigrant asteroids, bodies scattered from the outer solar system during planetary migration. Their composition, often rich in carbon dioxide or other volatiles, may resemble aspects of Atlas itself, creating the rare chance to observe interactions between chemically analogous objects from different origins. The close passage to Mars on October 3, 2025, at 0.19 astronomical units, exemplifies the balance between risk and reward. Close enough for detailed observation by Mars-orbiting spacecraft, yet far enough to avoid significant gravitational perturbations. Data gathered from this vantage point could reveal fine-scale tail structures, jet dynamics, and plasma interactions inaccessible from Earth. Overall, the survival statistics strongly favor Atlas, navigating the asteroid belt intact, Celestial mechanics and spatial scales make catastrophic encounters with large bodies highly improbable. Yet even infinitesimal probabilities carry dramatic tension. Every day without incident bolsters confidence, while each sudden brightness spike or asymmetric jet reminds observers that interactions with unseen debris remain possible. These micro-events illuminate the hazards of a solar system filled not with solid perfection, but with countless small, high-energy projectiles capable of undoing a billion-year journey in an instant. Atlas has already endured extraordinary trials, eons in interstellar space, relentless cosmic radiation, and gravitational nudges from unseen stars in the galactic thick disk. Ironically, the final test might come from the humble debris of its adopted solar system, a gauntlet of dust and rock that has persisted since our sun's birth. Survival is probable, yet the narrative tension remains, heightening both the scientific value and the drama of each observation. Each day that Atlas navigated the asteroid belt, without incident, reinforced confidence that it would emerge intact, carrying its precious cargo of alien ices and dust toward the ultimate test of solar encounter. While collision scenarios remained conceivable, the overwhelming likelihood of survival meant that answers to questions older than humanity itself might soon be revealed. As Atlas's nucleus warmed under the sun's influence, it was no longer a simple icy rock drifting through space. It had become an intricate dynamic laboratory of plasma physics, a self-contained system in which fundamental forces, matter, radiation, and electromagnetism interacted in ways impossible to replicate on Earth. The transformation began with ionization. Ultraviolet radiation from the sun stripped electrons from gas molecules escaping from Atlas's surface. Carbon dioxide and water vapor, the main constituents of its outgassing, became positively charged ions suspended in a sea of electrons. This ionized gas, or plasma, behaved in ways vastly different from neutral matter, responding dynamically to electric and magnetic fields. The solar wind, a continuous stream of charged particles moving at hundreds of kilometers per second, did not flow passively around Atlas. Instead, it engaged in a complex electromagnetic dialogue with the comet's plasma. Newly ionized molecules were picked up by the solar wind's magnetic field and accelerated, a process known as mass loading. Imagine a river suddenly burdened with thousands of sandbags. The flow slows, bends, and reshapes. For Atlas, carbon dioxide ions, heavier than water vapor ions, amplified these effects, creating plasma phenomena unseen in previous comet studies. Observations from the Rosetta mission at Comet 67 P/Churyumov-Gerasimenko revealed that mass loading can deflect solar wind by over 45 degrees, bending the normally radial flow into intricate magnetic patterns. Waves, oscillations, and instabilities propagate both upstream and downstream, traveling faster than the bulk plasma itself, and effectively announcing the comet's presence before any physical contact occurs. For Atlas, moving retrograde through the asteroid belt, relative velocities with the solar wind were extreme, producing stronger wave activity and more pronounced deflections. The comet's tail became a cosmic windsock. Magnetic reconnection events could sever segments of the plasma tail, which drifted away while new sections reformed closer to the nucleus. These tail disconnection events, observed in many comets, create some of the most visually dramatic sequences captured by astronomical instruments. With Atlas's unusual CO-Thorfrich chemistry, the behavior of its plasma tail promised to be even more spectacular. Carbon dioxide ions follow spiral paths in magnetic fields differently from water ions, generating new instabilities and structures, offering a fresh window into plasma physics under extreme conditions. The dust environment added another layer of complexity. Particles within the coma acquired electric charges via ultraviolet radiation, plasma currents, and secondary electron emissions. These charged grains responded to electromagnetic forces in addition to gravity and radiation pressure, creating chaotic and sometimes unpredictable dynamics. Laboratory studies of dusty plasmas suggest such systems exhibit instabilities, waves, and collective behaviors, bridging the scales between atomic physics and astrophysics. Around Atlas, these effects played out across millions of kilometers, forming a natural laboratory invisible to Earthbound experiments. The solar wind conditions Atlas encountered were especially intricate. The ecliptic plane, where the comet traveled, contains the most complex magnetic structures, including sector boundaries, co-rotating interaction regions, and sporadic coronal mass ejections. Each phenomenon imposed unique stresses: sudden tail shifts during sector crossings, coma compression from fast wind overtaking slower streams, and tail disconnections when CMEs passed. Multiple spacecraft, SOHO, SDO, Parker Solar Probe, and Mars orbiters tracked these interactions from different perspectives, producing unprecedented three-dimensional maps of plasma behavior. These plasma dynamics were more than just scientific curiosities. The ionized environment around Atlas actively shaped its visibility from Earth. Charged particles carried not only atoms and molecules, but the electromagnetic signatures of truly alien chemistry. Every spectral line, polarization pattern, and brightness fluctuation transmitted information about materials formed around another star, now interacting with our local solar environment. As the comet delved deeper into the asteroid belt, plasma interactions intensified. A growing coma provided more material for ionization, higher solar radiation, increased chemical activity, and the inner solar system's magnetic complexity amplified tail dynamics. The plasma environment could either stabilize Atlas, preventing fragmentation, or contribute to structural stress, hastening potential breakup. By this stage, Atlas was no longer simply a comet. It had become a self-contained plasma laboratory, executing natural experiments in fundamental physics, while racing through one of the most perilous regions of our solar system. Observers worldwide watched not only a visitor from another star, but a live demonstration of how matter, magnetism, and radiation interact on the grandest scales. With every day that passed without catastrophe, confidence grew that Atlas would survive its perilous journey through the asteroid belt, delivering its alien cargo intact and revealing secrets older than humanity itself. The possibility of collision with a massive asteroid remained, but the real threats were far subtler and potentially more insidious. While astronomers often imagine dramatic head-on impacts with large asteroids, the most significant dangers lurk in the fine-grained material filling the belt. Between Mars and Jupiter, countless particles, ranging from minuscule dust to pebble-sized fragments, zip along at high velocities. This ceaseless bombardment creates a cosmic sandblasting environment that could gradually erode Atlas's surface and the priceless chemical information it carries. Unlike catastrophic collisions, these micro-impacts are tiny in scale, but their effects accumulate. Each particle delivers energy proportional to the square of its speed. At typical belt velocities, even micrometer-sized dust grains strike like bullets, sputtering away surface layers and potentially exposing previously buried materials. This process, known as space weathering, has been altering celestial surfaces for billions of years, darkening them, forming microscopic glass spheres, and masking original chemical signatures. For Atlas, carrying interstellar material, such erosion could slowly destroy evidence before we have a chance to study it. Yet micro-impacts might also work in our favor. If Atlas carried a radiation-darkened crust from its eons in interstellar space, dust collisions could peel back this outer layer, revealing fresher, volatile-rich materials beneath. Some of the irregular jets and sudden brightness changes observed may already reflect this process. Tiny impacts exposing ices that quickly sublimate under sunlight. Thermal stress added another layer of danger. As Atlas neared the sun, its surface warmed rapidly, while the interior remained cold, creating steep thermal gradients. These stresses could crack the surface, allowing trapped volatiles to erupt as sudden jets or outbursts. History warns caution. Comet CL 2019Y, for Atlas brightened dramatically in 2020, only to fragment into dozens of smaller pieces due to internal stresses amplified by solar heating. Similarly, Comet Thiessen in 2013 appeared dazzling until tidal forces and extreme solar radiation destroyed it entirely. Atlas's unusual Su-Havrich composition complicates predictions. It could either suggest a robust, radiation-hardened crust or a fragile, highly volatile interior. Age might be an ally or an enemy. Its survival over billions of years implies resilience, yet repeated cosmic ray exposure and thermal cycling could have left it brittle, vulnerable to fragmentation under intense solar heating. Observations are beginning to reveal internal stresses. Sudden brightness spikes, asymmetric jets, and irregular coma density hint at episodic material release rather than steady outgassing. High-resolution imaging from Hubble and ground-based adaptive optics allows detection of subtle signs, multiple condensations, elongation of the nucleus or nascent secondary fragments, potentially signaling the onset of structural failure. External pressures compound these risks. The dense dust environment of the asteroid belt increases the likelihood of high-speed impacts with the coma or nucleus. Micro-impacts could locally heat the surface, triggering explosive outgassing, particularly in a CO2-rich nucleus, where lower sublimation temperatures can lead to more violent responses than typical water-dominated comets. The surrounding dust bands and zodiacal cloud also create spatially and temporally variable particle densities, meaning Atlas might encounter fluctuating bombardment conditions that directly alter its tail and brightness. Ironically, these hazards also present unprecedented scientific opportunities. Dust impacts could expose interior material, scattering previously hidden compositions into the coma, where telescopes can study them. The asteroid belt might act as a natural probe, gradually revealing Atlas's chemical makeup. Timing is critical. Each week of survival extends observation windows, but deeper penetration into dense dust regions increases the chance of stress-induced outbursts or fragmentation. Atlas is charting a course no interstellar visitor has traversed before. Unlike Oumuamua or Boris, it navigates a dense, particle-rich environment while actively outgassing. Its survival depends on a delicate balance between internal structural integrity, chemical composition, and cumulative external stresses. Every observation matters. Every brightness fluctuation could signal the comet's endurance or its potential collapse. Micro-collisions and dust, while less spectacular than catastrophic asteroid strikes, might prove decisive in determining whether Atlas survives to reveal its secrets or slowly disintegrates under the relentless pressures of the solar system. By July 2025, as telescopes worldwide focused on the interstellar visitor, a provocative study captured headlines. A preprint by Abraham Lowe and colleagues presented a speculative scenario. What if Atlas was not a natural comet at all, but an artificial construct? Could this ancient wanderer, with its unusual chemistry and precise trajectory, be a product of intelligent design, perhaps even with unknown intent? The idea wasn't entirely new. Abraham Lowe had earlier suggested that Oumuamua's odd acceleration and lack of detectable outgassing might hint at artificial origins. Atlas, however, presented a subtler puzzle. Unlike Oumuamua's visibly active, developing the coma and tail expected of a natural comet, yet its path and timing seemed almost perfectly suited for detailed observation. The paper presenting this hypothesis was carefully qualified, framing the possibility of an artificial object as just one of many explanations. But in the media landscape of 2025, nuance often vanished. Tentative speculation was rapidly transformed into sensational headlines. Tabloid coverage amplified every hint of mystery, while opinion pieces extrapolated far beyond what the original authors proposed, creating a feedback loop of ever more dramatic claims. The scientific community responded swiftly and cautiously. NASA classified Atlas as a natural comet, citing early spectroscopic measurements that detected standard cometary volatiles, albeit in unusual ratios. Observations from the James Webb Space Telescope confirmed the presence of carbon dioxide and water vapor, consistent with natural sublimation processes, even if the relative abundances were atypical. Crucially, no signs of artificial construction had been observed. Radio surveys detected only thermal emissions. Light curves matched the irregular rotation of a natural nucleus, rather than a symmetric engineered object, and no anomalous acceleration beyond normal outgassing was recorded. Arguments about seemingly convenient timing also faltered under scrutiny. While Atlas's near-ecliptic, scientifically rich trajectory did place it in ideal observational regions, this was not necessarily evidence of design. Orbital mechanics constrains the paths interstellar objects can take, and objects are most likely to be discovered where telescopes can see them. The Mars flyby at 0.19 astronomical units, cited by some as suspiciously precise, is in fact a common distance for hyperbolic encounters. Human instrumentation merely happened to be in the right place to capitalize on the opportunity. SETI researchers, while skeptical, used the speculation as an opportunity for focused monitoring. Radio telescopes worldwide conducted opportunistic observations during the Mars flyby and the comet's solar approach, searching for any signals that might suggest technological origin. No transmissions, no trailing probes, and no structured anomalies in the coma or tail were detected. Spectroscopic measurements further supported a natural origin. Carbon dioxide-rich chemistry, though unusual for local comets, is consistent with formation in the outer regions of other stellar systems. Isotopic ratios, when measurable, reflected standard nucleosynthesis, rather than the engineered signatures one might expect from artificial constructs. The episode underscored the challenges of interpreting truly anomalous data. Interstellar visitors like Oumuamua and Atlas can display behaviors beyond the range of solar system experience, demanding careful distinction between genuinely exotic natural phenomena and potential artificiality. It also highlighted the role of media literacy. Speculative academic discussion can easily be misinterpreted as proof, especially when cultural frameworks of alien probes and first contact already shape public perception. Ethical considerations also emerged. Were concrete evidence of artificiality ever found, scientists would need to coordinate disclosure and communication internationally. For Atlas, however, the evidence overwhelmingly favored a natural explanation. Its rare chemistry and trajectory, while remarkable, could be fully explained by natural processes in distant stellar nurseries. The real mystery lay not in whether Atlas was controlled, but in understanding how other star systems produce such unique, long-lived interstellar travelers. Even the most resilient comets are vulnerable when exposed to the intense conditions of the inner solar system. For Atlas, subtle changes signaled the beginning of a possible unraveling. Initially it was slight, minor brightness fluctuations, irregular jets, and asymmetrical coma structures. Gradually, these hints escalated. Internal pressures from sublimating volatiles, amplified by the thermal stresses of solar heating, began to exploit ancient fractures in the nucleus. Cometary fragmentation is both violent and visually arresting. As heat penetrates the core, trapped ices vaporize, generating pockets of pressure that push against the rigid ice rock matrix. Cracks formed over billions of years become conduits for sudden explosive outgassing. When these pressures exceed structural limits, the nucleus fractures, chunks separate, each carrying its own trajectory, forming a rapidly expanding cloud of debris. The disintegration is slow motion yet spectacular, a billion-year-old interstellar wanderer torn apart by forces it had never previously encountered. This process highlights the delicate balance that governs comet survival. Even the most ancient, durable interstellar objects can be undone not by catastrophic collisions, but by the gradual accumulation of internal and external stresses, solar radiation, dust impacts, thermal gradients, and volatile sublimation. The spectacle is both a loss and an opportunity. While the intact nucleus disappears, the debris cloud exposes materials from deep within the comet, offering a final glimpse into alien chemistry that had traveled across the galaxy. Since the discovery of the first interstellar object, people have speculated wildly, could a comet like Atlas be caught by our solar system's gravity, abandoning its hyperbolic flight to linger among the planets? The idea is tantalizing, appealing to a deep-seated desire for cosmic neighbors. To imagine a billion-year traveler choosing to settle in our familiar solar neighborhood is irresistibly romantic. Physics, however, is less sentimental. Atlas hurtles through space with a hyperbolic excess velocity of roughly 58 km/s, an energy level that no planetary encounter could meaningfully dissipate. Even Jupiter, our system's most massive planet, can only adjust an object's speed by a few kilometers per second during a close approach. Compared to Atlas's enormous kinetic energy, these interactions barely alter its course. Permanent capture would require the object to shed more than 99% of that energy, a feat impossible without mechanisms far beyond what our planets can provide. Gravitational encounters can produce subtle trajectory tweaks. Mars, at a flyby distance of 0.19 AU on October 3rd, may slightly adjust Atlas's path, altering the timing of perihelion or the exit angle from the inner solar system. Venus, at 0.65 AU later in November could introduce additional minor perturbations. Even combined, these influences do little more than nudge Atlas along its hyperbolic trajectory. They cannot trap it within the solar system. Non-gravitational forces, however, play a more nuanced role. Outgassing jets act like minuscule thrusters, exerting continuous acceleration that can subtly alter a comet's orbit over time. Atlas's unusual carbon dioxide-rich composition might produce asymmetric jets, unlike typical water-ice comets, introducing measurable, if modest, adjustments in trajectory. Historical missions like Rosetta demonstrated how such forces can shift orbital periods and positions over successive orbits. For Atlas, these effects may slightly change the exit vector or rotation, but they cannot overcome the enormous hyperbolic momentum carrying it outward. Speculative scenarios imagining Atlas hiding within the asteroid belt as a resident object are equally unphysical. Hyperbolic trajectories do not allow for permanent solar orbits regardless of location. Post-perihelion observations, scheduled for early December 2025, will provide high-precision tracking to detect any deviations caused by planetary encounters or outgassing. These data will refine our understanding of non-gravitational forces and inform models for future interstellar visitors. Observation opportunities are extensive. Spacecraft throughout the inner solar system can track Atlas from multiple angles, providing parallax measurements and revealing even small trajectory shifts. Mars-orbiting instruments such as MAVEN, Mars Reconnaissance Orbiter, and ESA's Mars Express, along with surface assets like the Perseverance rover, can contribute to a detailed record of the comet's motion and brightness. These observations help scientists quantify how interstellar objects respond to stellar environments, enhancing predictions for the behavior of future visitors. Ultimately, Atlas will leave our solar system, still traveling along a hyperbolic path. Planetary encounters and outgassing may tweak its exit trajectory and timing, but the fundamental outcome is immutable. It will return to interstellar space. There is a bittersweet quality to this certainty. While we cannot keep this extraordinary visitor for extended study, we can take solace in the fact that it continues its journey across the galaxy, carrying the chemical signatures of alien systems to future stellar neighborhoods. Atlas, in this sense, serves as a cosmic ambassador. Its brief visit connects distant stars, allowing a transfer of material and information on scales that dwarf human experience. Redirection fantasies, compelling though they may be, cannot overturn the immutable laws of celestial mechanics. The comet remains a traveler, not a resident, a fleeting, luminous messenger that leaves behind invaluable data, unforgettable observations, and a reminder of the vast, interconnected web of our galaxy. What began in July 2025 as a single carefully worded preprint had evolved into a sprawling, sometimes contentious public debate by the time Atlas reached the asteroid belt. Abraham Lowe and his colleagues had framed their paper as a pedagogical exercise, exploring the extreme possibly hostile, as a way to illustrate how extraordinary claims require extraordinary evidence. Their language was cautious, designed to provoke thought rather than assert fact. Yet, in the age of social media, measured scientific speculation quickly mutated into sensational narratives. Algorithms favoring engagement amplified the most dramatic interpretations, often stripping away the hedging and probability assessments that were central to the original work. Headlines suggested certainty where none existed, and casual readers interpreted possibilities as facts. The scientific community maintained a disciplined, evidence-driven approach. NASA classified Atlas as a natural comet, supported by multiple observational lines. Spectroscopic data from the James Webb Space Telescope, alongside ground-based observatories, matched expected sublimation processes, even if the ratios of volatiles differed from familiar solar system comets. Most critically, none of the indicators of artificial origin, controlled acceleration, structured outgassing patterns, geometric features, or coherent radio emissions were detected. SETI researchers seized the opportunity to conduct targeted passive monitoring. Programs like Breakthrough Listen, scheduled observations during Mars flyby, solar approach, and post-perihelion exit, hoping to detect any potential communication. The lack of signals, while not a definitive disproof, provided no evidence supporting the technological hypothesis. Similarly, high-resolution imaging and adaptive optics campaigns found no secondary objects, deployed devices or patterns suggesting intentional engineering. Isotopic analyses reinforced the natural explanation. Carbon, oxygen, and hydrogen ratios aligned with models of stellar nucleosynthesis in alien systems, rather than the unusual signatures that might arise from constructed materials. In short, the alien hypothesis remained a speculative exercise without empirical support. The surrounding cultural context amplified the story. Previous debates over Oumuamua had primed public imagination, while science fiction offered ready frameworks for interpreting anomalies as alien probes or surveillance devices. In the media, uncertainty was often replaced by narrative certainty, illustrating a broader challenge in science communication: how to responsibly convey speculative science in a world of instantaneous amplification. Yet the controversy offered opportunities for education. It became a vivid case study in the scientific method, demonstrating the distinction between hypothesis, testing, and verified knowledge. It highlighted the ethical dimensions of discovery, particularly regarding disclosure, international coordination, and public communication in the event of genuinely anomalous findings. Most importantly, the alien speculation underscored how remarkable Atlas was on its own terms. Its unusual chemistry, near-ecliptic trajectory, and timely discovery were not evidence of technology, but of natural processes operating in stellar environments far removed from our solar neighborhood. Carbon dioxide-rich composition, atypical isotopic ratios, and orbital geometry revealed behaviors and histories beyond anything seen in local comets. The natural universe, it turned out, was strange enough to inspire wonder without invoking alien engineering. Atlas's detection was more than an astronomical curiosity. It was a harbinger of a new era. Interstellar visitors, once exceedingly rare, may become routine targets of observation. Current sky surveys, impressive though they are, capture only a fraction of the objects passing through our neighborhood. Most catalogued objects, near-Earth asteroids, Kuiper Belt residents, and distant solar system bodies, are gravitationally bound, following predictable orbits. Interstellar interlopers, in contrast, arrive unpredictably, trace hyperbolic paths, and are visible for only brief windows. The discovery of Atlas, like its predecessors Oumuamua, Borisov, and others, relied as much on chance and timing as on systematic search programs. Yet this is poised to change. The completion of the Vera C. Rubin Observatory, formerly the Large Synoptic Survey Telescope, heralds a dramatic shift. Beginning operations in the mid-2020s, the facility will conduct a decade-long survey of the southern sky, imaging the entire visible universe every few nights with unparalleled depth and precision. This next-generation survey promises to detect interstellar visitors routinely rather than sporadically, providing extended observation windows, better characterization of compositions, and precise tracking of trajectories. Atlas is a glimpse of what is to come, a wake-up call reminding humanity that the cosmos is teeming with wandering worlds, each carrying unique stories of formation, evolution, and chemical history. The era of fleeting interstellar encounters may soon give way to a sustained and systematic exploration of objects that have journeyed across the galaxy, offering insights into alien stellar systems without leaving the comfort of our own solar neighborhood. The arrival of Atlas signaled more than a single astronomical event. It was a glimpse into a future where interstellar visitors may appear with growing frequency. Current surveys, impressive though they are, primarily detect solar system residents, asteroids, Kuiper Belt objects, and distant dwarf planets, all moving along predictable orbits. Interstellar travelers, however, arrive from random directions, follow hyperbolic paths, and are typically visible for only short periods. The discovery of Atlas, like Oumuamua and Borisov before it, relied as much on chance as on careful observation. That is set to change with the Vera C. Rubin Observatory. Rubin Observatory, formerly the Large Synoptic Survey Telescope, starting in the mid-2020s, this revolutionary facility will systematically scan the southern sky, capturing the entire visible universe every few nights with unprecedented clarity and depth. Estimates for detecting interstellar objects vary widely. Conservative models suggest 1 or 2 per year, representing a tenfold increase over current discovery rates. Optimistic projections based on theoretical models of galactic object populations predict dozens of detections annually once the survey reaches full capacity. The scientific implications are immense. Each new object brings unique chemical fingerprints and formation histories from stellar systems far beyond our own. With a growing sample, astronomers can uncover patterns, test models of planet formation, and explore galactic chemical evolution in ways impossible from single observations like ATLAS. Increased detection rates also introduce operational challenges. ATLAS benefited from months of coordinated observation across multiple observatories, both ground and space-based. In a future of frequent interstellar visitors, automated detection, rapid response protocols, and flexible scheduling will be essential. Lessons learned from ATLAS, including coordination between NASA, ISA, NIA and international partners, demonstrated how the global astronomical community can mobilize efficiently when rare opportunities arise. The rapid redeployment of assets like the James Webb Space Telescope and Hubble underscored the value of adaptable observation priorities. The experience also highlighted public communication. ATLAS generated enormous attention, evolving from technical discovery notices to sensationalized media coverage. Future encounters will require careful messaging to balance excitement with accurate scientific context. Planetary defense considerations further complicate the picture. While ATLAS posed no threat, future interstellar objects could follow trajectories that intersect or closely approach Earth. Rapid orbit determination and size estimation will be crucial for assessing any potential hazards. Technology is beginning to meet these demands. Machine learning now allows survey data to flag moving objects with accuracy, approaching that of human analysts. Automated systems can trigger follow-up observations based on predefined criteria. Global communication networks can disseminate alerts within hours of discovery. The educational benefits are profound. Each interstellar object serves as a natural classroom for exploring stellar formation, planetary dynamics, and galactic chemistry. Their diversity, ranging from familiar comet-like bodies to completely alien constructs, provides an unprecedented laboratory for comparative studies on a galactic scale. Data management will be a growing challenge. Observations of each visitor generate terabytes of imaging, spectroscopic, and photometric information, all of which must be archived and made accessible for future research. ATLAS's dataset now serves as a benchmark for interpreting future discoveries and testing theoretical models. International collaboration will be increasingly important. No single observatory or nation can fully characterize multiple interstellar visitors simultaneously. Coordinated telescope time, shared expertise, and global observation networks will be essential. Technological implications extend to spacecraft and mission planning. Should interstellar objects become common, rapid response interceptor missions could be deployed, allowing spacecraft to rendezvous with newly discovered visitors. Concepts for such missions already exist, awaiting sufficient detection frequency to justify implementation. Even amateur astronomers will play key roles. Modern equipment and computer-controlled telescopes have made it possible for distributed networks of enthusiasts to provide continuous monitoring, supplementing professional facilities with limited telescope availability. Ultimately, ATLAS's appearance is a wake-up call, not just about observational readiness, but about our place in the galaxy. These travelers remind us that we are part of a vast cosmic ecosystem, where materials and potentially life move between stars over millions or billions of years. Each interstellar visitor carries fragments of other worlds, distant chemistry, and a connection to stellar processes beyond direct human reach. ATLAS has already begun this lesson. Future visitors will complete it, transforming interstellar objects from rare curiosities into familiar representatives of the galaxy's shared heritage. Humanity is learning to expect the unexpected and to recognize the vast, interconnected nature of the cosmos. As ATLAS completes its passage through the asteroid belt and approaches its October solar encounter, it carries far more than ancient ice and alien compounds. This celestial wanderer has become a reflection of humanity's own understanding of the universe. Through its journey, we glimpse a cosmos far more intricate, dynamic, and interconnected than earlier generations could have imagined. ATLAS is not merely a visitor, it is a mirror, showing us how our solar neighborhood fits within the grand tapestry of the galaxy and how even brief encounters with distant worlds can expand our sense of perspective and wonder. Whether Atlas survives its journey past the sun intact, gradually melts under the intense heat, or shatters into a brilliant display across the sky, it has already accomplished its most essential role, serving as a messenger from the stars. Every spectrum captured, every photometric measurement, and every structural observation gathered by our instruments adds to a growing understanding of how material travels between stellar systems, carrying chemical fingerprints from distant worlds. Its retrograde orbit, threading through the densest regions of our solar system, reminds us that cosmic traffic moves in every direction, guided by gravitational forces operating on galactic scales. The same principles that govern planetary motion around the Sun also shape the paths of interstellar wanderers, creating encounters like Atlas that connect star systems separated by light years. Its unusual composition, a carbon dioxide-rich signature recorded by the James Webb Space Telescope, offers a rare glimpse into the conditions under which planets form around stars unlike our own. The ratios of volatile compounds, isotopic abundances, and physical characteristics all point to environments where temperature, radiation, and chemical makeup combine to produce bodies unlike anything in our solar neighborhood. There is a subtle beauty in this natural diversity. What may appear extraordinary is simply nature operating under slightly different conditions, refined over billions of years of cosmic evolution. Atlas is entirely natural. It is a product of stellar processes, yet these subtle variations have created an object that challenges our understanding of planetary formation and galactic chemistry. On a philosophical level, observing Atlas expands our perspective on the universe and our place within it. Studying this object is like reading a story that began when the galaxy was far younger. The material we see today was formed billions of years before Earth even existed. Each photon reflected from its nucleus, each spectral signature analyzed, links us to processes from epochs long past. In this sense, we are not just looking at distant light, we are directly examining matter that has preserved the chemistry of ancient stellar environments. The technological coordination behind these observations demonstrates humanity's growing mastery of the cosmos. By combining data from space-based telescopes, terrestrial observatories, and sophisticated models, we can analyze objects moving at tremendous speeds in exquisite detail. We have become cosmic historians, uncovering the life stories of matter older than our species. Yet Atlas also underscores how little we truly know. It is just one sample among countless interstellar objects in the Milky Way, each carrying its own chemical makeup, history, and mysteries waiting to be uncovered. Practically, Atlas provides a glimpse of the future when facilities like the Vera C. Rubin Observatory will detect interstellar visitors routinely rather than by chance. The observation techniques, global coordination, and public communication strategies trialed during its passage are a rehearsal for managing future cosmic arrivals. Safety concerns, always a consideration with approaching celestial objects, are already resolved. Its closest approach of 1.8 astronomical units keeps it safely distant from Earth. Even if it fragments completely, the debris will continue along the same hyperbolic trajectory, exiting the inner solar system without posing a threat. Freed from safety constraints, scientists can focus solely on the opportunity to study it. Culturally, Atlas shifts our understanding of humanity's place in the galaxy. This passage demonstrates that our solar system is not isolated, but receives regular visits from matter formed around other stars. Dust and gas released from its surface will join the zodiacal cloud, mingling interstellar materials with local debris. Future spacecraft, and perhaps future human explorers, will encounter these particles without realizing their extraordinary origins. Atlas embodies both arrival and departure, visiting briefly while leaving a lasting imprint on our local environment. It will carry solar wind traces into interstellar space, while leaving behind matter that permanently enriches our corner of the cosmos. Even as it approaches perihelion, the most profound lessons are already apparent. Atlas confirms the existence of a chemically diverse population of interstellar bodies. It demonstrates that natural processes in distant stellar environments can create materials that challenge our theoretical models. Most importantly, it shows that our solar system participates in a larger interconnected network of material exchange spanning the galaxy. As Atlas recedes, whether whole or fragmented. It leaves a transformed sense of humanity's place in the Milky Way. We are not isolated observers, we are participants in galactic processes, linking star formation, planetary evolution, and chemical cycles across vast distances. This ancient traveler conveys a message in the universal language of physics and chemistry, one that we are only beginning to decipher. The message is clear. We are not alone. Our very matter travels the galaxy, connecting distant stars to our own world. Atlas functions as a cosmic mirror, reflecting connection rather than isolation, participation rather than uniqueness. The face it reflects is both familiar and extraordinary, ancient yet eternal, local yet universal. And as one visitor departs, another is already on its way, carrying fresh stories from stars we may never directly observe, continuing an interstellar dialogue written in the timeless language of wandering worlds.